Assalamualaikum. Good morning, everyone. We're still talking about kinetic analysis for rigid body, specifically on work and energy approach. We are saying that our system is conserving the energy, so basically work and energy can be interchanged. So in our system, we can have work done to it or change in work done, and this change in work done will be equal to change in energy in the system, and the change in energy in the system can comes from three sources. Okay, the first one, change in gravitational potential energy, which is due to the change in height. And then we have a change in elastic potential energy, which is due to the change in spring length. And then we have change in kinetic potential energy, which is due to the change in velocity. In the case of particle, we have done the same analysis. However, we limit ourselves to certain things. For example, in the case of particle, we are saying that this delta U, or change in work done, can comes from cable, it comes from external force. Our delta Vg comes from change in height. Our delta Ve comes from change in spring length. Delta T comes from change in velocity. Be more specific, linear velocity V. Okay, this is what we have used in particle analysis using work and energy approach. In rigid body analysis, instead of having just these two, I missed another one here from friction as well. For a rigid body, we have additional terms here, which is external moment. We can have work done coming from external moment. In terms of change in gravitational potential energy, we still use the same equation. However, to be more specific, when we say change in height, refers to CG location, not just any position, but at CG location. So we'll be referring to components with masses, okay? And these components will have its own CG location, and the change in the height will be referring to this CG location. Next, we have a change in spring length. The equation is still the same for particle and rigid body, and the implementation is still the same. Nothing changed here. Right. As for the change in kinetic energy, we know that for a rigid body, it can move in translation motion, can has linear velocity, it can also has angular velocity as well. So in that sense, we have change in velocity, not only linear velocity, but also in angular velocity, omega. Okay, why is that? Because our rigid body can translate as well as rotate. Right? In terms of equation itself, delta U equals to, if we are talking about force, times delta S. If we are talking about moment, times change in angle. Okay, and if we are talking about cable, again we have force times delta S, or force times delta L, or the change in the length of the cable. As for delta Vg, it is equals to mg times delta H, and this H will refer to CG location. As for delta Ve, it will be equals to half A x2 minus x1, same as before, whereby x is our change in spring length. For delta T, initially our equation is just delta T equals to half m v2 squared minus v1 squared. Okay, this is our initial equation that we use for particle. For rigid body, we have additional term, which is another half I omega 2 squared minus omega 1 squared. And not only that, to be more specific, in this case, the velocity is velocity at the CG location, the second position, and at the CG location for the first position. As for the I is applied at the CG. Okay, so this will be our delta T equation. Okay, once we have known all of this, we can straight away use the equation inside our problem. What happens if you forgot about this? We can use our kinetic energy terms there. We know that T is equal to half mv squared, and if we replace the velocity equals to omega r inside this equation, we will have half m omega r squared. Okay, and since mass is acting at the CG, the velocity must be velocity at the CG as well. So we can expand this. We'll have half m omega squared r squared, and mr squared is our I. And since the velocity is at the CG, this I must be at the CG as well. Okay, so our kinetic energy can be written in this form, which is half mvg squared, or half mv squared, or can also be written as half ig omega squared. Okay, if the object is only translating, we can use t equals to half mv squared only. If the object is only rotating, we have t equals to half I g omega squared only. However, if the object is both translating and rotating, just like what we have for a body moving in general motion, so we have both terms inside our potential kinetic energy equation. So that's why we have both terms here. Once we are clear about this, we can refer back to our question. The challenge for this type of question is to determine what will be the condition for position 1 and position 2. Okay, once the conditions are clear, the rest is just the matter of solving the problem. So in this case, we have two links, OA and BC. Only OA and BC have mass attached to them. So bear in mind with that. We were told that OA will have angular velocity of 1.5 radian per second at position 2. Okay, whereby link BC will be in horizontal position. So at position 2, BC will be in horizontal position. And we were told that the system is being released from a rest position as shown in the figure. So the figure is showing position 1 or the initial position whereby everything is in rest, initially in rest. So basically, initially in rest means it's not moving yet. We were asked to calculate what will be the stiffness of the spring. If it will be compressed by 5 centimeter as shown. Okay, and the mass of the collar and friction can be ignored or neglected. Okay, so our work energy equation is just delta U equals to delta Vg plus delta Ve plus delta T. Okay, so this topic for me is easy, especially in terms of getting marks, because solving delta U will be separate from delta Vg, it will be separate from delta Ve, and it will be separate from delta T as well. So you have 4 components that can be solved separately, and they are not interrelated. That means if you don't know about one of the component, or you make a mistake in one of the component, it will not affect the rest. Okay, the rest will be fine. All right. So it's easy to get marks for this topic. Okay, but make sure you do revision as well. Okay, don't take it easy. All right. So we have to recognize what will be the position. So we have position 1 as shown, and then position 2 whereby member BC or link BC is horizontal. So in this case, we want BC to be horizontal, and at the same time, the collar will compress the spring. So the only possible solution will be the solution that I shown in the slide here. Okay, we cannot have member OA rotating clockwise. Okay, and BC is on the other side of the figure here. Okay, we cannot have something like this. For example, member so we have OA, and then B is here. So this is BC. Collar is attached to C. Then we have the rod, the spring at some distance away. Okay, we cannot have this condition. Okay, why? Because at this instant, the collar is not compressing the spring. Okay, we want the collar to be compressing the spring at position 2. Why is that? Because we want the spring to be compressed. Okay, at position 2. So this will be the condition at position 2. Right? So you have to read the question carefully and determine what will be the position of the members within certain mechanism at position 1 as well as at position 2. Once that is clear, half of your problem is solved actually. Okay, but if you make a mistake on this, I would say more, well, in terms of equation might be correct, but the rest are all wrong because it's based on wrong position. Okay, so we look at delta U first. We know delta U is coming or can come from friction, external force, external moment, or cable. And ask ourselves, do we have any of this? If we don't have any of this, if we don't see any external force, external moment anywhere, there's no force being applied through cable, no friction, so straight away we can say that our delta U is equal to 0. Then we move on to the next one. Normally after delta U, I will always try to solve delta Vg first, because naturally this is the easiest one to solve, because you just need to know mass, where the mass is acting, and you have to look at the change in height for the mass, right? So we have two members with mass, MOA and MBC. Okay, so we can ignore the rest. We can ignore the collar because there's no mass attached to the collar. Okay, so member OA is a rod. So for a rod, we know the CG location will be in the middle of the rod. Okay, so we have CG of the OA here in the figure, and also CG for BC will be at the center of BC as well. Okay, and we have two positions, position 1 and position 2. So the CG is changing in height from position 1 to position 2. Okay, the first step is to determine what will be the change in height. Okay, so look at the CG of OA. So CG of OA is changing from a higher position or higher ground in position 1 to position 2. Okay, so the change is negative change because the height is reduced. Okay, never mind. That will be counted by the sign of delta H. Okay, so for OA, we'll have mg delta H, which is equal to 0.9 times 9.1 times minus 0.25. Okay, how do I get this minus 0.25? Coming from the length of OA, then divided by 2. Right? So that will be the change in the height for CG of OA. And then for member BC, we have the change of height equals to half of 40 centimeter here, which is minus 0.2. Right? So calculate this, we'll have minus 3.973. And since we have two rigid body with masses, okay, so our terms will be expanded to 2. One covering OA, while the other one is covering BC. Okay, if we have more than 2, so you'll have more than 2 mg delta H equation to be considered. Alright, so this one for me is pretty straightforward for delta Vg. You just need to know what's the CG location, what is the change of height for the CG location. That's it. Okay, once you know that, you can calculate delta Vg straight away. And bear in mind, if the CG location is getting higher, delta H will be positive. If it is getting lower, delta H will be negative. Next, we have delta VE. Okay, so delta VE is covering the change in spring length. Okay, or it depends only on spring. If you see a particular question without any spring, so straight away you know delta VE is equal to 0. Okay, unless you have something that behaves like a spring, then probably you can use delta VE equation there. But most of the time, in our question, delta VE comes only from spring. Okay, so again, we have to look at position 1 and position 2, compare what happens in position 1 and in position 2. So in position 1, the spring is as shown here. Okay, in position 2, what happens to the spring? The collar will compress the spring by 5 centimeter. Okay, so X is our change in spring length. Right, so to stress the fact, X is change in spring length. And not just any change, it must be from original length. Okay, from the original spring length. Right, so in this case, X2 is the change in spring length at the second position, or basically when it's being compressed. In this case, we were told that it will be compressed by 5 centimeter. So spring length is being reduced by 5 centimeters, so that's why I have minus 0.05 here in meter. Okay, this will be our x2. As for x1, at this instant in time, the spring is being free. Okay, nothing is doing anything to the spring. Okay, so whatever the spring length here is the original spring length, and it's not given. And to be honest, we don't care because we just want to know what's the value of x. We don't want to know what's the original value of the spring length. Okay, so at the first instant, we know that the spring is not compressed or elongate at any way. So x will be equal to 0. Okay, so x will be equal to 0 since let's say for position 1, x1 for example, this will be equal to length at position 1 minus the original spring length. Okay, and since these two is the same, L1 and Li is the same, so x1 will be equal to 0. Okay, for position 1. So k is not given yet. Let's calculate the equation for delta VE, which is 1.25 times 10 power of minus 3k. Okay, so that's it. Next, we move on to delta T. Okay, for delta T, we know that we have two rigid body with mass. Okay, so we'll have two equations. One is covering OA, the other one is covering BC. Okay, for each one of them, we'll have the term corresponding to linear velocity and the term corresponding to angular velocity. Okay, so generally the equation is half m v2 squared minus v1 squared plus half ig omega 2 squared minus omega 1 squared. Okay, or if I want to make this more general, instead of writing it like this, I can also write in this form. Okay, delta T is equal to T2 minus T1, right? So what is T2? What is T1? Okay, T2 will be equal to, since we have two rigid body here, half m v at the CG of 2 squared plus I at the CG omega 2 squared. This is for member OA. Alright. Plus same term mv at the CG 2 squared plus I half I at the CG of omega 2 squared. This is for member BC. This is the T2 term. And of course we have the same term for the same form of equation for T1. Just substitute 2 for 1. Okay, so we have half m p at the CG at the first position plus I at the CG omega at the first position for member OA plus half m p at the CG for the first position plus half I at the CG omega at the first position squared. This will be the term for BC. In this case, we were told that the system is being released from rest, means it is initially not moving. Not moving means that the velocity is 0. When velocity is 0, omega will also be 0. Why is that? Because we know V is equal to omega R. If V0, omega 0. So straight away, if it is being released from rest, we know that at the first instant, or at T1, V and omega will be equal to 0 for both OA and AB. So straight away, T1 is actually equal to 0 for this particular example. Or if you are familiar with the delta T equation, you don't want to write it in this form, you can also use delta T equals to this, put everything inside one big equation, and then by knowing that the system is being released from rest, just cancel out the first the velocity and omega term that correspond to the first position, which is Vg1 and omega 1. Okay. Since we know that the mass is acting at the CG, the velocity must also be velocity at the CG. Okay, and I that we want to consider is I at the CG, or mass moment of inertia for axis that is passing through the CG. Okay, so remove these terms, we are left with just the term for T2. Okay, so in this case, only T2 terms exist for both OA and BC. Right. So to solve this, we have to do velocity analysis. Okay. The velocity analysis should be done for position 2. Why position 2? Because only T2 exists here. So everything must be done for position 2, meaning you have to refer to the figure corresponding to position 2. Right? So at position 2, we know how member OA moves. OA is rotating. We are not interested with all the points. We are interested only with the CG location for both member OA and BC. Okay, so member OA is rotating about O, so the CG of OA must be rotating about O as well. So we have path of motion for the CG OA, and this is the velocity of the CG OA. Right? 90 degrees with respect to the radius. Okay, and this will be equal to omega OA times the radius, which is given by 0.5. That's it. Okay. For the CG of BC, okay, BC is a member that is moving in a general motion. Why? Since B is rotating about O, C, on the other hand, is sliding, or C is moving in a rectilinear motion. Okay, or in a translation motion. So we have BC that is moving in a general motion. So if BC is moving in a general motion, we have to use two approach to do the velocity analysis, either using I or using relative acceleration equation. In this case, the easiest way is to use I. So how to find I? We know point C. Okay, point C is moving in a linear motion or translation motion. So the line of velocity of C is known. So this is the line of velocity for C. Okay. The line of velocity for point G is also known here. Okay. So based on these two velocity lines, we can construct perpendicular lines that will intersect each other. So perpendicular line for point C is this line. Perpendicular line for the CG location will be this line, and we can see that it intersects point C actually. Okay, so C happens to be our I location, and we know the velocity here will be equal to 0. Okay, velocity at C will be equal to 0 since it behaves like our instantaneous center of zero velocity. Okay, velocity at the center of rotation will be equal to 0. So straight away we know velocity at C is equal to 0. How about velocity of the CG for member BC? Okay, in this case we have to use this I again. Okay, we know at this instant in time BC seems to be rotating about I. Okay, so point B seems to rotate about I. CG of BC also seems to rotate about I as well. Okay, so we have to determine that first. Okay, how to determine that? We have to know what is the velocity at point B first. Okay, and velocity at point B is equal to omega OB times the radius. Okay, it's getting cramped here. Let's say I put down here. Velocity at B will be equal to omega for member OA times the radius in this case, which is 0.4. Okay, And we were told that at position 2, omega OA is given, which is equal to 1.5 times 0.4. So this will be equal to 0.6. Right? Once we know VB, we can use this VB information to determine what will be the omega for member BC at position 2. Okay, so the same VB can be obtained by using member BC, which is equal to omega for member BC times the radius, okay, of B from our center of rotation, in this case, point I here or point C here. So the length BC is given, which is equals to 0.5 meter. Okay, so straight away we know that 0.6 will be equal to omega BC times 0.5. So omega BC will be equals to 1.2. Right? This is the value of omega BC. Okay. So once we have omega BC, we can determine what will be the value of the velocity at the CG of BC. Okay. So our aim here is to determine this guy, velocity at the CG of BC. Alright. Why we want to determine velocity at CG of BC? Since we want to use this inside our delta T equation. Okay. Let's remove this first. So the velocity at the CG of BC will be equals to omega for BC times the radius, which is the distance from CG of BC to C, or basically half of BC, which is equals to 0.25. So we will have 1.2 times 0.25. This will give us 0.3 meter per second. Okay, so done. So we have determined what will be the velocity at the CG of OA and also velocity at the CG of BC. Oh, I didn't calculate what is the velocity at the CG of OA. Okay, velocity CG of OA will be equal to omega OA times the distance from CG of OA to point O, which is equals to half of 40 centimeter, which is 0.2. This will give us 1.5 times 0.2 is equals to 0.3 meter per second again. Okay, so substitute back inside our delta T equation. So delta T equation is delta T equation. So it will be equals to half the mass VG2 for member OA. For member OA, it's 0.3 plus I at the CG for member OA. Okay, in this case, we just have a rod, so I at the CG of the rod, which is perpendicular to this plane, will be equal to ml squared over 12. So we have 0.9, the length, which is 0.5 squared over 12 for the half. Omega 2 is omega of member OA. Okay, omega is not point dependent, it is body dependent. So it's omega for member OA at position 2, and that omega is given here, which is equals to 1.5. Okay, the actual direction of omega, either clockwise or anti-clockwise, not so important. Okay, you can say clockwise positive or anti-clockwise negative. In the end, when you square the value of omega, both of them will give you the same answer. So don't bother with the direction of omega. So this is the term for member A, and then we have another term for member BC. Again, the same mass. Velocity at the CG for member BC is still 0.3. That's half. I at the CG will still be the same, since both of OA and BC are rods and having the same length. As for omega for member BC, okay, omega BC is equal to 1.2 radian per second. Here 1.2. Alright, so calculate this. We'll have delta T for this position, or basically position 2. So I got 0.116 joule. Okay. Right. So once we have our delta T, we can go back and put everything inside our main equation, which is this equation. So what we'll have, delta U is equals to 0, delta Vg is equals to minus 3.973, delta VE 1.25 and power of minus 3, and our delta T is equals to 0.116. So rearrange this guy. Well, we'll have K equals to, okay, so this is the value of K, 0.5.6 Newton per meter. Alright. If somehow when you solve problem like this, whereby you need to find what is the stiffness value, somehow if you got K equals to negative value, you should stop and go back, check back your answer. Okay, because spring stiffness should be positive. Okay, can it be negative? Well, to be honest with you, yes. Okay, it can be negative, but for special type of spring, normally spring stiffness will be positive. Okay, if you have a negative spring, it means that the behavior will be the opposite as what we know for conventional spring. Okay, for conventional spring, if you push it and let it go, it will bounce back. Okay, but if you have K that is negative, it will behave in the opposite way. Okay, so make sure your K is positive, just like mass, for example. Okay, mass should be positive. If you somehow calculate mass equals to a negative value, something must be wrong somewhere.